these in descending order, largest to smallest. Today is the second, and you just, changed your answer. So remember, the thing to do is take all the ones that are in one either period or group and put them in order. Then, because I'm always giving you one oddball that's either in a different group or a different period, then you're going to compare that to whatever it has something in common with. So in this case, it's really easy to line up the group 1 stuff. You're just going bottom to top. They're bigger at the bottom, they're smaller at the top. And then you have to look at silver and say, well, silver's in the same period as rubidium, and because it's further this way, it's going to be smaller. So that's good. All right, level of confidence on that? Okay. So we're going to introduce a new concept with the periodic table that's very similar to this. Let's start off with this question. Are you familiar with the term ion? Who thinks they know what an ion is? With better than 50% certainty. Okay. What do you think an ion is? You got stuff to add to that. We've got that one. We may have more before we're done. What do you remember about ions from physical science? So we have a nomination for, do you want to make the pronoun they more specific? So you want to say like ions have a positive charge? Okay. So we have another piece of information added here. Again, anybody want to add, subtract, modify, completely negate? So we have another suggestion that an ion is when what gains or loses? Something gains or loses what? Gains or loses charge. Okay. All right. So, anything else we want to add to that? Subtract from that. Modify that. What we have so far is that an ion is an element with a different number of electrons than is common. An ion is when something gains or loses charge. We're not sure what. An ion is when an atom loses an electron, and ions have a positive charge. Do you want to add anything to that? Do you want to subtract anything from that? Do you want to clarify anything? Do you want to completely throw anything out? There are no names attached here, so you can say, "Brah, that's ridiculous." Anybody ever listen to Car Talk, Saturday mornings, WYSU? They're going off the air now. The one brother died a couple years ago, and they've been doing reruns for a few years. They would always do a weekly puzzler, and every time the one brother would present the solution to the puzzler, and they were funny little puzzler things, and if the other brother didn't like it, he'd always go bogus for the answer. So anybody want to call one of these just completely bogus and throw it out altogether? Anybody want to modify anything? Anybody want to add anything? Clarify anything? Some of you have that face that I know I make when I'm thinking, but I'm not ready to say something, which is the pinchy-lipped face. I don't know if that's I'm thinking about it, but I'm not saying it yet. I'm not ready. Anything. Do you think any of these are totally wrong? Do you think any of them are complete and totally right and they leave nothing out? Bark, bark, bark. So you chicken to commit to a position. Okay, so let's go from what we've got. Okay, so what we have so far, element with a different number of electrons, ions have a positive charge, atoms lose an electron, ion is when something gains or loses charge. So I'm going to circle the things that I think are closer to complete and total than other things. I really like this one. I really like this one. Those are good. Those come closest, though they're not total. They're not all the way there. These are saying the same thing. And there's one significant issue with them. They tell half the story. Okay, now with that information, can you go further in developing your definition of what an ion is? Okay, so that pretty well completed the thought. These two are the flip side of the other coin. When an atom loses an electron, it has a positive charge. When an atom gains an electron, it has a negative charge. And it's true that in all of those cases, what we now have is an atom, and I would sub out here for element the word atom. And later on we'll get into even bonded groups of atoms that can gain or lose electrons. So yeah, in either of those cases, you now have an atom with a different number of electrons than, we could say common, but I would rather say than what we're used to thinking about, or a different number of electrons than protons. And this is good. We could leave that there if we put the word atom in. So, now that we've had this little talk, what's an ion? So the simplest definition of ion is a charged atom. An atom that has gained or lost electrons. An atom that is not neutral. Okay. Good. Now, to go back to prefixes, suffixes, and roots. Do you guys do that in English at some grade level? Intensively? Zation. Blankization. Okay. Ionization. Blankization typically means what? I can't think of a good example right now to save my life. Yeah, the creation of something. I'm thinking like, cakeization. Okay, that's stupid. The process of turning something into a cake. Okay, so this is going to lead us right straight to ionization. So we said ization is, the process of creating something. So we're going to talk about ionization. And ionization is the process of making an ion. And we said that an ion was an atom that had gained or lost electrons. So really, ionization is the process of gaining, adding or subtracting an electron from an atom. And what we're going to talk about first is ionization energy. And that is where we are stripping off an electron. So if we subtract an electron, do we make a positive or a negative ion? Positive. And if you struggle with that one, you're not the only one, and I have a nice little mnemonic of doing pluses and minuses and seeing how they cancel out. Cancel, 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 still neutral. But if we take away an electron, then they no longer cancel, and we have a positive charge. Of course, it's not going to show that. Ionization energy is just IE, and it's really important to understand and to remember that ionization energy, we are only here, though we can make a positive or a negative ion, when we talk about IE, we're only talking about stripping an electron off of an atom. So the energy change that occurs with adding an electron is a whole different thing. And we mostly talk about ionization energy at this level. So IE is all about stealing electrons. There's a song in there someplace. It's like some sort of heartbroken love song, do me wrong kind of, probably a cheating song. Oh, it could be a country song. There could be cheating, there could be revenge. You could form positive ions. Come on, somebody's got to do it. Okay, so ionization energy has trends that, remember, there are like 4 billion layers of information on this thing, and ionization energy is one of them. There are trends in ionization energy that line up perfectly with the periodic table. Freaky, isn't it? Okay, so here's my weird, cool, somewhat trippy picture. Energy levels. Whose model is this? Bohr. That's right. So that's our sort of generic old Bohr model of an atom. Well, ionization energy has some periodic trends. In group 1, heck, they'll pay you to take their electron. They will give it up like nobody's business. Here, you're driving by, take my electron. They will throw their electron at you. They don't want that extra electron. They have the lowest ionization energy in their period every single time. Halogens, on the other hand, group 17, won't give up an electron for anything. You would have to pry it out of their cold, dead fingers. But there's one that's even harder than the halogens, and that's the noble gases, because the noble gases are totally satisfied, absolutely happy. They're not giving up anything. And if we look across a period, what we tend to see is that ionization energy tends to go up as we go across a period. It gets harder and harder to strip an electron off of an atom. So we can add to our little map, IE goes up as we go that way across the periodic table. And I would encourage you to add that to the top of your periodic table. That as we go across a period, IE increases. What did we say was happening with atomic radius as we went across a period? So the radius goes down as the ionization energy goes up. What a weird coincidence. Think there's a coincidence? Go for it, Michael. The relationship between ionization energy and atomic radius is no coincidence. What did we say affected atomic radius? How tightly the nucleus can pull in on those outer levels? Well, the more tightly that the nucleus can pull in, the harder it is to get that first electron pulled off. The looser the grip on those outer energy levels, the easier it is to knock an electron off. They tend to lose electrons very easily. And if you remember electron shielding. So if we go to this, Bohr model, and let's look at something whose electrons are located only on the first. Well, let's look at lithium. There's lithium. Okay, so looking at lithium, we only have one electron on the outer energy level. It's only shielded by one layer in between the nucleus, the pole of the nucleus, and that outer layer. It gives up that electron pretty easily. And as a matter of fact, if it could get rid of that electron, what would its configuration be? Just like. If it lost that one S, so look on your periodic table, if it lost that one S, or 2S1, what would it be? Helium. Everyone wants to be like a noble gas. And as a matter of fact, a neat little trick is if you write the noble gas configuration for something, and you look at whatever comes after the noble gas, that's typically the thing that gets given up in group 1 and group 2. Now, not in group 16, 17. If we look at beryllium, it's got 2 electrons on that outer level. So there's a little bit more to get a grip on. Now, it still gives up those 2 electrons, but it's not quite as easy as it is to strip the electrons from lithium. Okay, let's look at fluorine in this group. So I'm going to copy that, paste it. So fluorine, of course, is the absolute opposite end. 1, 2, 3, 4, 5, 6, 7. And in the case of fluorine, you've got huge sort of grip on that outer energy level. It's very difficult to remove an electron from fluorine. As a matter of fact, it doesn't happen. Fluorine, just as a rule, does not give up electrons. And if we write the noble gas configuration for fluorine, you'll see why. Oops. So we have helium, then we have 2s2, 2p5. And you kind of know this, you probably learned this in physical science. Fluorine is 1 electron away from a totally stable configuration. But it can't get it by going backwards. It can't go all the way down to helium. Even though it's a better configuration to be at, losing an electron still takes energy. It still takes energy to just strip an electron. So for lithium, the energy to lose 1 electron, that's minor, that's fine, and it gets to the stable configuration it wants to be at of helium. For fluorine, it would have to have 7 electrons stripped from it before it would be at a stable configuration. Much easier to add 1 electron and end up looking just like neon, to fill that 2p subshell. Yes, sir? Okay. So what would you expect in a period? Where would you expect? I'm going to put the blank periodic table up again. In period 3. Well, no, let's look at period 5. We'll go down to period 5. What the heck? Go crazy. Where would you expect the highest ionization energy in period 5 to be? And you can look at the one with names if you want to name it. You just give me a group number. 18, followed by 17. So the highest would be here. So if we're looking at, high energy listings, number 1, number 2, number 3, it goes right backwards. So the highest energy is always going to be your noble gas, whatever the noble gas in the group is, followed by the halogens, and then it's just sort of a sliding board down to group 1. Now, what did we say about atomic radius going down groups? What does it do? Atomic radius down a group, so radius down a group increases or decreases? Increases. So what do you think happens to ionization energy as you go down a group? It decreases. It gets progressively easier to strip electrons from those larger atoms as we go down a group. So let's actually look at group 1. Lithium, sodium, potassium, rubidium, cesium, francium. I like saying francium. I would love to name it. I could name a dog francium. I wouldn't name a child francium. But okay. The ease with which they lose electrons dictates their properties and dictates how reactive they are. So, here's sodium, here's rubidium. Which one do you think gives up electrons more easily? rubidium. Because, and let's look at that sort of Bohr model again. Hey, it's actually working. Copy. Shoot. Paste. So if we look at sodium, it has outer electrons on the 3rd main energy level. So it's got one hanging out there on the 3rd level. Still within reach of the nucleus. Still able to be sort of tended to and herded. If you look at rubidium, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Its last electron is all the way out there. What do we call that? Electron shielding. So we'll pick it up on Monday, and then you'll do a FIP quiz.